with arrows representing the flows of mass and energy among the different parts. This essentially represents a static model of what Earth's climate system looks like, which helps us get started thinking about it. The next step is to try to represent how the mass and energy flow through the system, turning this into something dynamic that can change over time. We'd use what we know about physics, chemistry, and biology to give the model information about how different processes work and how fast and under what conditions. So we're giving the model information about how to deal with stocks and flows. Typically, this is done using a bunch of equations, which represent stocks, flows, and feedbacks, including timescales on which different processes operate. And then the equations are solved by a computer. Once we've built a model, and it seems to operate with reasonable stability, then we could add, for example, some kind of perturbation. Then, if our model does a decent job of linking the different parts together, we could see how that perturbation ripples through the system and affects other parts. We could see whether and how fast the system approaches some equilibrium again, and what processes were largely responsible. We could actually turn different processes on or off to try to isolate their influence on the system. Again, something we can't do on the real planet. We also test our climate model's output against observations of the real world. And we might find out that the model aligns well with those observations, or we might find out that we need to revise the model, or maybe that we need to go out and make some more real-world observations to get a better handle on how things really work. Here's an example. We might find out that we need to revise the model, or maybe that we need to go out and make some more real-world observations to get a better handle on how things really work. Go out and make some more real-world observations to get a better handle on how things really work. Go out and make some more real-world observations to get a better handle on how things really work. Here's an example of a real-world constraint on climate models that has to do with the relative proportions of liquid water and water vapor. At warmer temperatures, more of the water present will be in vapor form, and at colder temperatures, less of the water present will be in vapor form, and more will be as liquid water or even solid ice, which isn't shown here. If a model is trying to represent what happens to water cycling through the climate system, it would have to take into account how the proportion of vapor to liquid changes if the temperature changes. If some air warms up in the model, then the model should also make some of the water in that air change phase from liquid to vapor, within some range that makes physical sense. If some air cools, as is common and as air rises through the atmosphere, then in the model, some of the water vapor present in the air should condense. Using a relationship like this, which is based on observations in the real world, a modeler can tell the model what to do with water as temperature changes. This is just one example of how observations help inform what goes into climate models. There are many more, like the rate at which CO2 exchanges with the ocean, or the heat capacity of water, or the average growth of trees each year, or the temperature profile of the atmosphere. Ideally, climate models align with physical reality. So, observations inform climate models, but climate models also can inform observations. For example, we've talked about how some of the excess CO2 emitted from human activities gets taken up by plants on land and some gets taken up by the oceans. With models and observations together, we can learn in more detail, more specifically, about where that carbon goes. Observations of atmospheric carbon dioxide in different parts of the world can be incorporated into models of atmospheric circulation, which tell us how the air moves around. And the output from those air circulation models can indicate which parts of the world are likely responsible for the uptake of CO2 from the atmosphere. Is it tropical forests? Is it certain areas of the ocean? The model output can actually help people decide in what regions of Earth would it be useful to conduct further observational work. Okay, to illustrate a climate model, using information we've encountered earlier, we're going to construct a simple energy balance model. This model uses essentially one physical relationship, and we've seen it before. It's the Stefan-Boltzmann equation, which relates energy output to the temperature of an object. You'll recall from earlier that warmer objects emit more energy, and that energy goes up as a function of the object's temperature raised to the 4th power. So it goes up exponentially as things heat up. We'll use that equation plus some addition and subtraction of energy flows to make this model. First, we'll start with something completely unrealistic. Imagine turning off the sun, so there's no solar energy coming in. We'll let the Earth's surface keep its tiny amount of geothermal energy coming from the planet's interior, about 0.06 watts per meter squared. With this little energy flow, Earth's surface has to emit 0.06 watts per meter squared to be in thermal equilibrium, and it can do that at a temperature of about 32 Kelvin, or about minus 241 degrees Celsius. Now we'll turn on the sun to its current energy output, which means Earth gets about 341 watts per meter squared. This is an example of an observation that's used in climate models. If we want to model the Earth, we need to use a realistic number for the incoming solar radiation. We'd use a different number if we were modeling Mars, for example. Okay, we're going to assume, for now, that Earth absorbs all the radiation it gets from the sun. Nothing is reflected, and there are no greenhouse gases. When the sun first turns on, Earth is emitting just 0.06 watts per meter squared, but now it's getting 341 watts per meter squared. So we have an imbalance. Over time, Earth warms up until it reaches the right temperature to emit the same amount of energy as it absorbs. That temperature, according to Stefan Boltzmann, where energy inflow equals energy outflow, is about 278 Kelvin, or about 5 degrees Celsius. So that's a very simple model, and it doesn't quite capture what's really going on. So let's add another important process, reflection. First, a question for you. What's going to happen to the temperature of our modeled Earth after we add reflection? Will temperature go up, go down, stay the same? What's going to happen? Today, Earth reflects about 30% of the incoming energy from the sun. So let's make our model do that. Now Earth's surface only absorbs 70% of what's coming in. So it only has to re-emit 239 watts per meter squared. And so it cools down to a new equilibrium, where energy inflow equals energy outflow, now at minus 18 degrees Celsius. So that's a little closer to representing the real Earth, and minus 18 Celsius is about the temperature of the upper atmosphere, and the temperature Earth's surface would be if we had 30% reflection and no greenhouse gases. Next step, add greenhouse gases. For our purpose here, we're going to make a simplifying assumption that the greenhouse gases absorb all the radiation coming from Earth's surface, and they re-emit half of it upward and half of it downward, just to make things conceptually more straightforward. We know that for the planet to be in energy balance, the upward emission from greenhouse gases will have to equal the solar inflow minus reflection. So that's 239 watts per meter squared. We've assumed in this model that the downward emission from greenhouse gases equals the upward emission. So that's also 239 watts per meter squared. So now Earth's surface is absorbing 239 from the sun plus 239 from greenhouse gases. So it has to re-emit 2 times 239 watts per meter squared back upward in order for inflow to equal outflow. And so it warms up to 303 Kelvin, or 30 degrees Celsius. If we take a look at what happens to our energy balance model over time, it looks something like this. From the left, we start just when we conceptually turn the sun back on, and suddenly inflow far exceeds outflow. The red line is way above the green line. Temperature is the blue line, and you can see the Earth starts off very cold, and it takes some time for it to warm up to its new equilibrium temperature with its new inflow of energy from the sun. When it does warm up enough so that inflow equals outflow, our model Earth's temperature stabilizes at about 5 degrees Celsius. But then we added reflection. So 30% of the incoming solar energy gets reflected away immediately, and our model Earth cools down to minus 18 Celsius. Then we added greenhouse gases to the model, and it warmed up again, and it stabilized at about 30 degrees Celsius once outflow caught up with inflow again. So one thing to notice is that there are transition periods in the model. When we change something, Earth doesn't respond immediately. There's some lag time before it reaches a new equilibrium state. Okay, so there's an example of an energy balance model with some assumptions and some simplifications. And this model produces a temperature for Earth's surface that we can compare to observations again and see how it does. Well, Earth's average surface temperature is about 15 degrees Celsius, not 30. So, how could our model get closer to approximating reality? Well, we could divide the atmosphere into layers and could more realistically represent the flows of energy due to greenhouse gases in the atmosphere, which aren't simply half up and half down. We could also take into account the fact that some energy emitted from Earth's surface proceeds directly to space. It doesn't all get absorbed by greenhouse gases. Or we could include that some energy leaves Earth's surface through latent heat transfer and thermals, not only via radiation. We could get specific about what's on Earth's surface. Is it water? Is it rock? We could make our energy balance model more closely approximate the real Earth by dividing our model planet into different latitude bands, not just treat the whole thing as one big average. The purpose of going through this model is to illustrate how we can use a few equations and construct a model that actually does approximate some of the processes happening on Earth. You could build this model yourself in a spreadsheet. With more sophistication, you could include more processes, giving them magnitudes based on observations in the real world, and bring your model closer to resembling reality. To summarize, with climate models, we're attempting to represent Earth's climate system. So it's important to ground the model in how physics, chemistry, and biology work in the real world. We use real-world observations to help define what's realistic in a model. And sometimes modeling can help us decide what new observations would be helpful. Ultimately, people build models to help better understand Earth's climate system. It's an ongoing effort. Hello and welcome. In this lesson, we're going to explore some of the choices climate modelers make. Climate models vary widely, from those that include few processes and average over large space and time scales, to those that explicitly attempt to model many interrelated processes and deal with smaller increments in space and time. It is impossible to truly capture a representation of the actual Earth, so modelers make choices. Their choices depend on the question of interest, and also are ultimately limited by time and computing power. Computing power does keep increasing, which increasingly makes it possible to add complexity to climate models, or allows modelers to increase spatial and temporal resolution, or to model longer time periods, or to run the model more times through. Here we're going to talk about some of the choices you might face if you become a climate modeler. The simplest kind of energy balance models, like we did before, basically average over the whole Earth and make some big assumptions. But those models are still useful to do things like estimate how long it might take for Earth to regain energy balance after a perturbation, or to estimate what might happen to Earth's average temperature if, say, overall reflectivity changed, for example. But we can get more complicated and model smaller scale processes if we conceptually divide Earth up into smaller pieces. The size of the pieces depends on what processes we're interested in studying. For example, if you're learning to identify continents, you don't need a particularly detailed world map. But if you're trying to find an address in an unfamiliar city, you need some small-scale detail. Here, one might choose to divide up the Earth into latitude bands. Just getting more detail by latitude can be informative because there are different things going on at the equator compared to the poles, particularly regarding energy coming in and leaving. The next step might be to also divide the Earth up by longitude and create smaller boxes instead of bands. You can imagine this grid over the surface of the Earth, and the model is keeping track of what happens in each grid cell. The cells are connected to one another, and they exchange matter and energy with one another. The boxes, or grid cells, can extend into 3 spatial dimensions. What's shown here is how one could divide up the atmosphere vertically too, so the cells stack on top of one another. Not shown here, but done in climate models that include ocean dynamics, are cells extending downward into the oceans as well. One detail to note on this image is that in the model, the chosen layers of the atmosphere are thinner near Earth's surface, where there are more molecules, and then the layers get thicker, so have less detailed resolution as you go up away from the surface. The same pattern is typically chosen in the ocean, where a lot of the action is closer to the surface layer, so it's useful to have higher spatial resolution there. Then they average bigger pieces deeper down in the ocean. The cells don't all need to be the same size. Also not shown here is surface topography, like mountain ranges, which stick up into the atmosphere and sometimes need to be taken into account, depending on what questions you're trying to answer. When should you stop dividing the Earth into smaller pieces in your model? If you model only the average Earth, you can address questions about the average Earth. If you want to answer questions about, say, temperature and precipitation patterns that happen on spatial scales of continents, you have to divide the Earth into enough cells that you can resolve the variations at the scale of interest. If you wanted to include hurricanes in your climate model, you need to have small enough cells to resolve hurricanes, and typically that would mean having at least 4 cells in the space covered by one hurricane, opposed to the cells around them. It would also be tracking motions from one cell to another, both horizontally and vertically, like the soccer players running around. Models can get more complex and can add more variables. People might add aerosols or dust or carbon to their models and track how those move around and influence other parts of the system. They might link their atmospheric model to a model of the oceans, which would track other variables, track how those move around and influence other parts of the system. More complex and can add more variables. People might add aerosols or ducts and can add more variables, and can add more variables, and can add more variables, and can add more variables. People might add aerosols or dust or carbon to their models and track how those move around and influence other parts of the system. They might link their atmospheric model to a model of the oceans, which would track other variables in each ocean cell, like temperature and salinity or sea ice at the surface. Each variable would be determined for each cell in the model at each time step. So each cell would just have one value for each of those variables for each time step. We wouldn't see any of the variation that might be happening at smaller scales. It would be highly unusual for a single model to include all the items shown in this cartoon of the climate system. And in fact, greater complexity is not necessarily helpful. There's way more going on in the climate system than any model can explicitly track. And there are important things happening at smaller spatial scales than the typical grid cell size of models, processes that turn out to matter on the larger spatial scale of the model. For example, photosynthesis is happening on really small scales, like the scale of a leaf, or if you want, even smaller than a leaf. Each leaf might not really matter for the climate system, but the aggregate effects of photosynthesis on the scale of a forest might be relevant. So there are choices to be made regarding at what level you explicitly model some of the processes in the climate system. Do you model each leaf, or do you make some reasonable assumptions and approximations and come out with an estimate of how the whole forest is interacting with the rest of the climate system? When modelers choose to approximate some process using reasonable assumptions and related variables, what they're doing is called parameterization. They're approximating aggregate effects and using those aggregate approximations in the model. Probably the most common example of parameterization in climate models is how people represent clouds. Clouds are tricky because they're typically smaller than a grid cell size, and cloud formation depends on lots of processes like evaporation and condensation that are happening at really tiny scales. We simply